Hello and welcome to this Edexcel Further Math Statistics 1 video looking at probability generating functions for some common distributions you've met. In order to derive a probability generating function, we need to know the standard formula for the distribution involved, and that means we need to know the general formula for the probability that a random variable from that distribution takes a specific value x. For example, for a binomial distribution, that probability would be ncx p to the x 1 minus p to the n minus x. So that's looking at x following a binomial distribution with parameters n and p. And we'll use the binomial as an example to work through on the next slide. So from the definition of a probability generating function, it's the sum over all values of x, and remember for a binomial distribution x can take the values 0 to n of t to the power x multiplied by the probability x takes a specific value, little x. And we need to substitute in that general formula for that probability, and we can then simplify that slightly because we have a t to the x and a p to the x, and we can put those two together as pt to the power x. And that's quite an awkward summation, but if you simply consider a normal binomial expansion a plus b to the n, where you would get a to the n plus nc1 a to the n minus 1b plus nc2 a to the n minus 2 b squared, etc. If you consider letting a equal 1 minus p and b equal pt, you will see that this summation here gives you exactly the same as the expansion of 1 minus p plus pt to the power n. And so you may well want to write a bit more out there to convince yourself of that. So we now have obtained the fact that the probability generating function for the binomial can be written like that, and in fact normally those brackets are omitted, and so this is the version you'll find in the formula book. So the generating functions for the other distributions that are involved in this course are given in the formula book, and the table is repeated here for you. You do need to be aware that although these are in the formula book, you should check in a textbook or online so that you are quite comfortable with actually deriving these probability generating functions for each of the distributions involved. And a few hints here. The Poisson derivation requires recognizing the power series for e to the power x. The geometric derivation requires using the sum to infinity of a geometric series, and the negative binomial distribution derivation is much more involved, but can be done by considering the variable x as a negative binomial variable also as the sum of a series of geometric variables. And for full derivations for each of those, you should look in textbooks or online. Let's look at some examples. So the first one requires us to find the generating function for a binomial, specific binomial distribution, and also show from the probability generating function that the probability x equals 3 takes a particular value. So this does require us to recall or look up the fact that the generating function for the binomial distribution is that. we can see quite clearly that the parameters for this specific binomial distribution are n equals 5 and p equals 0.2. So substituting that in the general expression for the generating function for a binomial variable, we get 1 minus p plus pt, so 0.8 plus 0.2t to the power 5, and expanding that you can see how the coefficient of each power of t is the binomial probability of getting that particular number of successes. And so for the last part of the question we want to show, so we do need to have things written out in full, that px equals 3 takes a particular value, so we actually need to look at one more term here, which would be this. So we want 3 successes, 0.2 cubed multiplied by t cubed, and if we've written that all out we can then say the probability x equals 3 is the coefficient of t cubed, which is this expression here, which indeed comes to the required 0.0512. Now the second example looks at a geometric distribution where the parameter is specified as 0.15, and that will require us to look up or remember that the generating function for a general geometric distribution is this expression here. And remember, you can find that in the formula book. And so substituting p equals 0.15, we can very simply obtain the probability generating function for this particular distribution. So something else that you are required to be able to do is to use a probability generating function for a known distribution so that you can obtain the mean and the variance of that distribution, and we're going to look at an example using the Poisson distribution. So the information required here is the expressions for Ex and the variance of x in terms of the generating function, and that we looked at in the last video, and we also require to know the generating function for the general Poisson distribution. And so in order to derive the mean for the general Poisson distribution, we need to take our generating function, and remember that we are differentiating with respect to t, so it's probably easier to write it in that form where e to the minus lambda is just a constant. So when we differentiate with respect to t, we will get lambda e to the lambda t, and that will still be multiplied by e to the minus lambda, and then when we substitute t equals 1, we will get lambda e to the lambda multiplied by 1 multiplied by e to the minus lambda. E to the lambda multiplied by e to the minus lambda is e to the 0 or 1, so we've very easily proved that the mean for the Poisson distribution is lambda. In order to find an expression for the variance for the general Poisson distribution, we are going to need to differentiate a second time and substitute t equals 1 and use this formula here. So going from the expression we had for the first derivative on the previous slide, if we differentiate that again, these constant terms will remain the same. And if we differentiate e to the lambda t, we get lambda e to the lambda t, and therefore substituting 1 in to that second derivative for t, we just get lambda e to the minus lambda, lambda e to the lambda, and that simply gives us lambda squared. Therefore the variance for the Poisson distribution would be lambda squared plus lambda minus lambda squared, which is equal to lambda. And that concludes this video. The next video will look at probability generating functions for the sum of random variables.